afternoon, everybody. Welcome to 2024 and the HGAC. And for the first colloquium this year, we have Ilya Mandel. From right away from Australia. Ilya, we've been trying very hard for many years, and we finally managed it. So we're extraordinarily happy to see you in person here in this hall. So for the formal introduction, I'll just hand over to the host.
Thank you very much. And it's a great pleasure today, and I'm told to speak into this computer so that your online audience can also hear us. It's a great pleasure to introduce Ilya to you. So Ilya has an interesting path in the sense that he did a degree, got a master's degree in computer science from Stanford University, but also he actually did a physics degree and the bachelor studies there. Thereafter, he moved not too far to Caltech to work on his PhD project with no one else than Kip Thorne, and graduated in 2008 to 2007, right? Thereafter, Ilya went further in the US to Northwestern University, to MIT, and from there on to the University of Birmingham in the UK, where you sort of worked up all the ranks to full professor. Then decided the UK is maybe too cold. You transition to Australia, where he's now based in Monash in Melbourne at the university. And Ilya has a long list of awards. I'm not going to actually read through them, but I would like to highlight maybe one or two aspects. So he's at the moment one of the chief investigators of the Australian Centre of Excellence for Gravitational-Wave Discovery, AusGraph, and this is a 70 million Australian dollar exercise. So it's a major effort, I think, to bring gravitational wave science forward. And among the sort of more scientific things, of course, Ilya has written tons of papers interesting to topics that he's going to discuss today. And he's also, for example, an editor for the Astrophysical Journal and also for the Astrophysical Journal Letters. So if you have any kind of questions, maybe on more kind of formal things, how things are being done, this is also maybe just for the more younger people. I mean, he's an expert also to talk to about such issues. And we're looking forward to your talking here. Thank you so much.
Thank you very much, Richard and Fabian, and it's a pleasure to be here. Thank you for your patience. I realized that because of the pandemic and a few other minor issues, my visit got delayed a few times, so I'm very grateful for your patience and, of course, for everybody coming today. So my plan is to talk a little bit about black holes and binaries, and I mean stellar mass black holes and binaries for the purposes of today's discussion. I should also say that I intentionally chose to include rather few slides to provide hopefully a setting and a venue for a conversation. So people should feel free to interrupt at any point if you have questions. You don't have to wait until the end. Even if I don't finish some of the slides, I'm not particularly bothered about it. I'd rather have a nice discussion. I'll actually get back to this picture in a moment, but this is a picture from a paper we had written a few years ago, showing perhaps some of the ways that you might end up forming the binary black holes that LIGO and Virgo have been observing through gravitational wave observations. But I'll get to that in just a moment. Let's actually start with perhaps a couple more general statements about observations first before getting into the theoretical modeling. So here's a nice plot courtesy of my colleague from Australia, from Curtin University in Perth, Arash Barhamian. So here, Arash has shown how many black holes we know about. And of course, the first stellar mass black holes, if we know these are stellar mass black holes, the first ones we know about come from X-ray observations. And these were starting in the late 1960s. The number grew steadily until it really skyrocketed with gravitational wave discoveries, starting with 2015, GW 150914 being the first one. And then in recent years, there's been another contribution coming from large optical surveys, including in particular observing black holes in detached binaries, observing stars moving around their companion black holes. Specifically looking at the gravitational wave observations, here's an animation courtesy of my collaborator Flor Brokharten. So this notice the scale is going to be shifting, and it's going to be shifting quite dramatically over time. So We'll go through this movie a couple of times, but you will see that the first gravitational observations started happening during the 01 science run, the first science run with advanced gravitational wave detectors. There were a couple of detections during that run, 02, 03. We are now in the 04 era. So, of course, anything beyond this point are just predictions. We only know of, firmly know the catalog of gravitational wave detections of binary black holes through 03. And we have some candidates that are publicly released from 04, but their properties will not be available until the LIGO-Virgo-Kagura collaborations complete analyzing the data. But it's safe to say that the catalog will probably at least double by the end of the 04 run, maybe more than that. And then, of course, there are some extrapolations going forward into the era of beyond advanced gravitational wave detectors. So there are proposals that people may know about to build instruments like the Einstein telescope, the Cosmic Explorer, maybe even before that, some upgrades to current detectors that go by a few different names, like a Voyager, A+, A Sharp, etc. There's still some discussion about exactly what form those will take. But again, the hope is that at least in the era of 3D detectors, so we're talking about timescales of 10 to 15 years, maybe 20 years from now, depending on funding and technology development, we are really hoping to be able to observe binary black hole mergers throughout the visible universe out to large redshifts. And this will mean that we're going from a few detections or a few tens of detections, or maybe a couple of hundred detections, which is the regime will be in at the end of the current 04 run, and all the way to hundreds of thousands, perhaps millions of detections. Now, where does it put us in terms of masses? Well, here's another plot from Monash, and it shows, again, the masses of black holes, of course, with error bars, observed through a variety of techniques. So, for example, microlensing observations are observations of staring at other stars and looking at the stars suddenly experiencing a brightening episode, brightening because there's a interloper object moving between the star and the observer. That object is lensing the light from the star. The duration of the transit is a function of the mass of the lens and the relative velocity of the lens of the star and the star. So there's some degeneracy there, but in general, knowing the mass of the lens, you can infer that in some of these cases, the lens's mass must be quite massive, too massive to be normal stars, because had they been normal stars with a mass of a few solar masses, you would have actually seen the lens itself. So it's a dark lens, which means it must be a neutron star or a black hole. And experiments like Ogle have observed maybe on the order of 20 such lenses, dark lenses quite confidently. There are ellipsoidal variations. There are astrometric measurements with instruments like Gaia. There are, of course, X-ray binaries. We'll discuss these in more detail in a moment, and gravitational wave sources. And of course, you can see that the mass ranges being probed are somewhat different. This is probably partly a statement about the fact that different ways of looking for black holes are sensitive to different kinds of black holes. But it's also partly, and I'll mention that in a second, but it's also perhaps a statement that there are evolutionary channels that are producing selection effects for or against particular masses. So let's focus specifically on X-ray binaries and gravitational wave sources. Many of you may have seen this kind of plot already. This is called masses in the stellar graveyard. This plot comes from Aaron Geller and collaborators at Northwestern. And the horizontal axis is just arbitrary, just for convenience. The vertical axis are masses. Now, this is a sort of logarithmic scale, not quite, but 1 solar mass, 2 solar masses, 5, 10, 20, etc., up to 100 solar masses. This is as of the end of the 03 run. Each little vertical combination here corresponds to emergent binary. So, for example, over here, this says that there was a merger of a roughly 7 solar mass black hole and a roughly 12 solar mass black hole, leading to a roughly 17 solar mass black hole. If you're wondering why the numbers I've just listed don't quite match up, it's not because my arithmetic is wrong. It's actually because you do lose about 5% of the mass energy to gravitational wave emission. So the mass of the final black hole left behind is about 5% lower than the sum of the masses of the two black holes that are merging together. The objects in blue are the merging black holes. So the tip of the arrow is the final remnant. The objects in orange are neutron stars. So in some of these cases, you're having mergers of two neutron stars. For example, this system here is GW 170817. Some people may recall that this was a very exciting system because it was not just a binary neutron star merger, but there was also a gamma ray burst observed, a short gamma ray burst, as well as a kilonova, as well as an afterglow from the gamma ray burst. And so this was probably one of the most studied transients of all time, observed in a variety of with a variety of instruments, of course, gravitational waves and electromagnetic observations, but also everywhere from radio to optical to X-ray to gamma ray frequencies in the electromagnetic spectrum. So this was, and of course, gravitational waves are able to actually provide us with estimates of the masses of the merging objects. So it's a really useful input to the electromagnetic observations that are telling us about the spectra and the light curves. This is, of course, leaving behind presumably a black hole in this case, although it's sort of colored in here as orange-blue, meaning let's be agnostic about whether or not it's a neutron star or black hole. And then in yellow, you have the neutron star masses observed in other ways than gravitational waves. So typically we're talking about radio pulsars and binaries, for example. And in magenta, you have the black hole masses from electromagnetic observations, typically from black hole X-ray binaries, which give you reasonably accurate mass estimates, although in some cases, these may also be astrometric estimates of black hole masses. Now, the reason I put in a few red circles over here are to immediately highlight a couple of possible points. So one point is there a mass gap between neutron stars, which mostly occupy the space between, well, let's say below about 2 solar masses, maybe 2.1 solar masses. It's still a little bit of a question how high neutron star masses can get. What is the maximum mass for long-term stable neutron star permitted by the neutron star equation of state? But it's probably somewhere in the ballpark of 2.1 solar masses. Certainly, most massive neutron stars seem to reach roughly those masses. And the lowest mass black holes, it used to be the case that X-ray binaries, low mass X-ray binaries suggested that black hole masses went down to about 5 solar masses. So there seems to be some mass gap here between 2 and 5 solar masses. That would be very interesting because it would suggest that there's something about the supernova explosion itself that favors the creation of a mass gap. So either you have a complete explosion that leaves behind just a relatively low mass, 1.4, let's say, solar mass, or 1.4 solar mass neutron star, I should say, or there is some fallback from the explosion, which leaves behind a more massive black hole. But now maybe there's some indication that there are objects sitting inside this mass gap. So perhaps this mass gap doesn't exist after all. There's another mass gap that has been suggested through theoretical modeling that should actually occupy this space out here. This is a mass gap from bare instability supernova. So the very simple idea is that if you have masses large enough, so we're talking about perhaps helium-4 masses of somewhere ballpark 60 to 120 solar masses, and this is very much ballpark. Different people have put in slightly different edges on that mass range, but the star gets so hot that you end up with explosive oxygen burning, and essentially the entire star becomes unstable and explodes at the end of its life, leaving behind no remnant. And then perhaps beyond that, on the upper end of the gap, you again can form black holes, but there should be sort of no black holes formed from single stars. This gap, as you can see, that does not seem to be the case over here. So we do seem to be seeing some black holes in the mass gap. There's an interesting question, of course, whether those are necessarily coming from single stars or not. So one possibility is that they are coming from single stars, and there's something that's imperfect about our understanding of parent stability supernova. Another possible explanation could be that there's a different origin for these black holes. So just to mention a couple of possibilities, maybe these are objects that form dynamically. So you could imagine for example, already merging two black holes. So if you start out with a 30 solar mass black hole and merges with another 30 solar mass black hole, we know that such things happen because this was more or less the first gravitational wave detection, was roughly two 30 solar mass black holes merging. Now you formed a 60 solar mass black hole. So now you do have a black hole in the mass gap. Now if somehow it manages to merge with something else, okay, now you might have a 60 plus 60 merger, right? Now how you get there is a separate story, but we can talk about that in a second. Another possibility is that black holes might be able to accrete. So maybe you start with a 30 solar mass black hole and you put it in some environment with plenty of gas. And well, you might have to wait for a while, because if you imagine that your black hole is limited to accreting the Eddington limit, then it takes several tens of millions of years to double in mass. But if you can willing to wait for, say, 100 million years, you might be able to do that. Now, where do you have enough of a supply of gas? Well, one possibility is you put it in an accretion disk in an AGN, right? So the lifetime of a typical AGN disk is about 100 million years. If you have a black hole that's embedded in the disk, then it has enough time to double in mass and go up to something like 60 solar masses, not a problem. So at least there are some possibilities there. Another thing you might notice is that there's a difference between the masses of the black holes like we're observing and the mass of the black holes that are seen in X-ray binaries. Now, part of that is just a selection effect. LIGO is sensitive. Gravitational waves are more sensitive to more massive systems, right? So if I have a more massive binary, it's a higher amplitude gravitational wave signal, so it can be observed further. So we're observing with gravitational waves a larger volume of the universe for these more massive black holes than for less massive ones. So all things being equal, in the gravitational wave catalog, more massive systems will be overrepresented. That's one explanation. But another explanation, for example, has to do with the evolutionary history of these systems. If you're looking at, for example, high mass X-ray binaries, you're really talking about systems that are only a few million years old, right? So if you are thinking, for example, of a black hole that's accreting from a massive star, and this massive star companion, let's say accreting winds from a massive star companion, this massive star is itself 40 solar masses, which is the case, for example, for the companion of Cygnus X1, the most massive known galactic Milky Way black hole, then that companion itself has a lifetime of only a few million years. So we're talking about young systems. Now, young means typically relatively high metallicity, right? Because metallicity increases over cosmic time. So you're looking at things in the nearby universe that are young, they have a high metallicity. High metallicity also means, in general, stronger winds, more rapid mass loss. More rapid mass loss means that even if you start with a high mass, you very likely end up, by the time you form a black hole, with a lower mass object. In fact, our models suggest that it's pretty difficult through, let's say, classical isolated binary evolution to form things at solar metallicities that would be much in excess of 20 solar masses in terms of black hole masses. So that means that in the local universe where velocity is roughly solar, this really is about as high as the black hole masses might be expected to get. What about these guys over here? Well, part of the answer is that LIGO, of course, can see further away. So some of these more massive systems can be seen out to redshifts approaching 1, even with the current gravitational detectors, and the redshift will go even higher as detectors become more sensitive. But another part of the story is that some of these things, even if they're emerging locally at smaller redshifts, can have very long delay times between formation and merger. Gravitational waves are very efficient at removing energy very late in the in-spiral, but early on, gravitational waves are actually very weak while the binary is wide. And so it can take a very long time for systems to merge through gravitational wave emission. So some of the systems that are merging, even in the local universe today, might actually have formed at high redshifts of 4 or 5, for example, just with very long delay times approaching the edge of the universe. And of course, at those high redshifts, the universe was much more metal poor, winds would have been suppressed, and so you end up with more easily forming more massive black holes. Now, this is not the full story, but this is part of a possible explanation for this discrepancy. Let's also think a little bit about black hole spins. Now, it's worth saying that we can't measure everything with equal accuracy when we talk about gravitational detections. In principle, yes, you can measure masses and you can measure spins. By the way, just to give you a sense of why you can measure masses, here's what a gravitational wave signal from a binary sounds like. Sorry, did it badly. Let me do it one more time. Here's what it sounds like for a binary black hole. The more massive a system is, the lower the final frequency that you end up reaching, because essentially, if a system is more massive, you can think about how high, if you want to sort of very roughly imagine how high the frequency can get, forget about general relativity, think about Keplerian orbits, but think about the fact that there is, in general relativity, there's something called the innermost stable circular orbit. That's as close as a point particle can get orbiting in the circular orbit before it plunges in. That's about 6 gravitational radii or 3 Schwarzschild radii away. So it's proportional. The smallest separation you can get before plunge is proportional to the mass. So higher mass means larger separation, which means because, okay, we know that the Keplerian orbital frequency is root gm over separation cubed. So in this case, separation goes as mass. And so that means that the frequency actually goes as 1 over mass. So that means that higher mass, the frequency never gets to be as high. There's also an impact on the mass of the mass on the rate of frequency evolution. In fact, the particular mass parameter called the chirp mass is a particular combination of the component masses, the mass of each component to the 3/5 power divided by the total mass to the 1/5 power. It's called the chirp mass, and that determines what is the how quickly the frequency is evolving. So these things can be measured pretty well. On the other hand, for example, the spins have a second order effect on the evolution. What the spin is going to do is it's going to create some additional modulation, for example, if there's some spin orbit precession. So instead of sounding like this, you might sound like this. So that little modulation might allow you to infer something about the spin, but now there are more degeneracies or correlations that come in, and so the measurement is not quite as accurate. So one particular combination of spins that is reasonably well measured is called the effective spin. The effective spin is a kind of mass-weighted component of the spin along the direction of the orbital angular momentum. That's probably the best measured spin component. You can see that there is, if you look at chi effective over here, this is unfortunately here it's not plotted in absolute units. The absolute units go between -1 and 1, but this is in plotted in terms of the uncertainty in the spin measurement. And you can see that basically everything that's sort of within 2 sigma is more or less consistent with a chi effective parameter of 0. And then there are a few values that clearly are sitting in the top right. So above that are no longer consistent with 0. So basically what we can say is that the spins for the vast majority of emergent binary black holes are consistent with 0, which could, for example, mean that the spins are just literally 0 for both components. Or it could be a statement that there is somehow funnily misaligned. Let's say both spins are in the orbital plane, or one spin is up, one spin is down, canceling each other. And for some binary black holes, spins are clearly positive. Where's that coming from? Well, one possibility is that, for example, if really we think that spins are most 0 for most black holes, that's actually not a crazy assumption to make, because you might imagine that if you're going to merge 2 black holes with each other, and at least you imagine these black holes have started out in a stellar binary, so this is what I'm referring to as isolated binary evolution, then at some point that binary is going to interact. There's going to be mass transfer from one component to another. Typically in a evolved star, in a giant or a supergiant, most of the moment of inertia is sitting in the envelope, because the envelope is far away. And so unless you have crazy amounts of differential rotation, most of the angular momentum is sitting out in the envelope. And if that envelope is removed because of mass transfer in a binary, then you remove the bulk of the angular momentum. So you leave behind a core which has actually very little angular momentum in it. And so that means the spin of a black hole is just a statement about the angular momentum in units of mass squared. So that means you leave behind very little angular momentum. So maybe all black holes should be very slowly spinning, at least those in binaries. But then you realize that, well, there's at least one caveat to that, which is that if at some point you have a, let's say, a black hole and nearby a naked helium star, and the naked helium star is so close to the black hole, so these are particularly exceptionally tight binaries. The helium star is maybe only about a solar radius in size, so the separation is only a few solar radii, so that the helium star is tightly locked to the black hole, then it's going to be, because of tidal locking, it's going to be rapidly spinning. So whatever the angular momentum was initially is going to be spun up by tides, and being spun up by tides can give rise to a relatively rapidly spinning black hole. Please. Please. Of course.
Yeah, so I'm a bit puzzled by this slowly evolving black hole, because if you look at how neutron stars, I thought that most neutron stars, they spin like crazy. So they're almost as radioactive when they form, and then they slowly slow down. So why would you expect that black holes have low angular momentum? Of course, most angular momentum is in the outer region of the star, but the core that collapses is collapsing by a factor of 1,000 or something in radius. So even if you have a little rotation, it will spin up.
So this is a very good point. So one of the statements is that the neutron stars are spinning extremely rapidly, and absolutely you may have very short rotational periods of milliseconds in some cases, right? But actually, even that is not necessarily in these crazy units of black hole spin parameters, is actually not all that high, strangely enough, because we're really talking about angular momentum here, and let's say the A pulsar in the double pulsar system JO737, which is has a orbital spin period of about 20 milliseconds, has a dimensional spin parameter of only about 0.03 or 0.04, depending what you assume for its moment of inertia. It's now you're right that in principle it's you can have situations where you can imagine that there should be enough spin in the progenitor. For example, if you somehow manage to keep the progenitor rapidly spinning by tides, or you can by accretion onto the progenitor, and certainly you can, it's not crazy to imagine that you have a Wolf-Rayet star with enough angular momentum that it's, let's say if a Wolf-Rayet star is spinning almost critically, it will give rise to a black hole actually with too much angular momentum. And so one of the conjectures is this is maybe how you form long gamma ray bursts from collapsars, that there's an excess of angular momentum in the collapsing star, and so you need to get rid of that angular momentum, and that's what's ultimately creating a jet and powering the long GRB. So you're absolutely right that this is a little bit oversimplified, but let's say it's not. Maybe I should have phrased it a little bit more differently. It's not crazy to imagine that you would have a significant population of rather slowly spinning black holes if you imagine that there's relatively efficient angular transport in the progenitors, and that you remove most of the envelope which contains the bulk of the angular momentum. A few words about black hole X-ray binaries. Well, let me mention particular Cygnus X1. It's one that I've worked on in recent years a fair bit, and of course I should say there are people in the audience who've been working on some of the systems for much longer than I have. I think Philip has been thinking about Cygnus X1 for at least 20 years, probably a lot more than that. There are a few interesting properties to this system. So one is the masses of the black hole. I mentioned that the masses have actually been recently upgraded thanks to some observational work by James Miller-Jones. So the masses are around 21 solar masses of the black hole and 40 solar masses of the companion. It's almost completely Roswell filling. So meaning that in this case, the O star 40 solar mass companion is almost, but not quite, at the point where its mass is being tidally pulled off by the tidal gravity of the black hole. But it's still nominally in the regime where it's actually the winds from the O star that are being captured by the black hole. Interestingly, this nearly complete Roswell filling is not unique to this wind-fed system, but in fact, most black hole X-ray, high mass X-ray binaries, wind-fed X-ray binaries, if we know, are almost completely Roswell filling. And maybe if I have time, I'll say a couple of words about that in a second, because I think we finally understand why that's happening. The system has a very low eccentricity that suggests that the black hole has experienced almost complete fallback. So there wasn't much mass lost in a supernova explosion. Probably wasn't an explosion period. Might just be consistent with a little bit of mass lost in neutrinos due to some 0.1 solar masses during the collapse. Well, perhaps not surprisingly, it's tidally locked. Okay, that's what you would expect given that it's such a close binary. There are another interesting observation is that, and this one, although I should say is a questionable one, but there's a lot of debate in literature about this, but there are some claims that some of these high mass X2 binaries, the black holes are rapidly spinning. In Cygnus X1, perhaps it's the spin parameter is above 0.95, where 1 is the maximum for a curved black hole, 0 is Schwarzschild not spinning. Similar claims of rapid spins have been made for M33X7, for LMC-X1. This is seemingly contradicting my previous statement that it should be difficult to have these black holes spin. There are some suggestions for how you might be able to do that, again, through tidal locking at just the appropriate time in their evolution. Another suggestion is that the measurements are wrong, because it's actually not that easy to infer the black hole spins from things like continuum fitting of the spectrum from the disk, or from iron K alpha reflection lines from the disk. There are some interesting observations of black hole binary systemic velocities. Some questions about what are the, at least in one system that has been explained, that there's a observed misalignment angle between the spin of the black hole and the orbit. So all of these are interesting observations creating additional puzzles. Microlensing I've already mentioned, so I won't discuss that in any more detail. Similarly, for astrometric observations, this is an example of one by Ted Thompson and collaborators from 2019. So let's step back for a moment to this question of like observations of merging binary black holes. And my first statement is going to be binary black holes shouldn't merge. Well, you already know that's the wrong statement, but let me tell you why it's the first statement that should come to mind. As I mentioned, it's actually not very easy to get black hole binaries to merge because gravitational waves are not very efficient for wide enough binaries. For simplicity, ignore the lines here corresponding to non-zero eccentricities, focus on the top one. So this is, imagine you have a binary eccentricity of 0. Imagine, for simplicity, you have equal component masses. So the horizontal axis here, that just shows the component masses. And in that case, the ordinate shows the maximum value of the orbital separation such that the binary could still merge within the age of the universe, within 14 billion years, through the emission of gravitational waves, right? So the way to read this thought is to say, okay, if I have a 30 solar mass binary, 30 solar masses with 30 solar masses, then the separation cannot be more than about 40 or 50 solar radii, so a quarter of an astronomical unit or a fifth of an astronomical unit. If I want this binary, even if it was formed right after the Big Bang, if I wanted to merge by today and therefore be detectable by gravitational waves. Of course, it can be smaller, which would mean that there's a smaller delay time, but it cannot be any larger than that if I want this to merge through gravitational waves. For binary neutron stars, separations are even smaller, we're talking about a few solar radii. So I need a very tight binary. Meanwhile, I ask myself, how large do massive stars typically get at their greatest extent during their evolution? Well, okay, you can quibble about whether this particular set of stellar models is accurate or not. And the answer is it's not. But you know, the ballpark numbers are roughly in the right place in the sense that we're typically talking about several hundred solar radii at maximum extent, perhaps over 1,000 in some cases, meaning several astronomical units. So we have two stars that at some point are going to get to be this big, and we want them to be in a binary that's this small in order to merge within the age of the universe through the emission of gravitational waves, right? It's kind of hard to, it's not quite fitting a square peg into a round hole. It's more like fitting a, peg this big into a hole this small, right? Try to put infant shoes on an elephant or something like that, right? It doesn't quite work. So binaries shouldn't merge. Well, of course, we know they do. Don't worry, I'm not expecting that anybody will be able to read this list or for that matter, that plot. This is just by way of illustration and also to show that I have to apologize in advance that most of my slides don't include references because there's so much work on this, but the references, if you want them, are in this review that Thor Carton and I had written, I guess, 2 years ago now. And this shows the various predictions for the rates of formations of binary black holes through a wide variety of channels. I'll mention a couple of them in a second. And this shows some of the many papers that have been written on these topics, including by many of the people in this audience or in Heidelberg. So, for example, some of these papers are from Michele Mappelli and her group. Some of these papers are from Fabian and Philip and collaborators, etc. So how do you generally do this? Well, let me at least briefly summarize a couple of options, right? So option number one, I start with a wide binary, and then I bring the binary together at just the right moment. So there's a little bit of magic involved. I bring it together at just the moment when the stars are already compact, so they don't have this issue of trying to fit stars this big into a binary this small. So start with a wide binary. one star maybe transfers mass onto its companion. After it expands, fine, the binary still stays wide. Then maybe this first star, the primary, the more massive star initially, which also evolves faster, creates a black hole. Then the secondary expands. And when the secondary expands, it starts transferring mass onto the companion. And perhaps during this stage, you develop what's called a common envelope. So common envelope meaning that the mass transfer is dynamically unstable. The more mass is being transferred, the faster you want to transfer mass. If that happens, the companion is engulfed in the envelope of the donor. There is, of course, if there's a lack of co-rotation at this point, then there is drag, there's friction. This friction is heating up the envelope. Fritz is hiding because he is probably very bothered by the fact that I'm explaining the mysteries of common envelopes in such a hand-wavy way. So my great apologies to Fritz and other people who work closely on this. But as a result of this friction, you're, of course, heating up the envelope. You're losing orbital energy, so the orbit is shrinking, dumping that energy into the envelope. The envelope expands in response to the energy insertion into the envelope, and eventually you might succeed in expelling the envelope altogether. If you succeed in doing that, you've gotten rid of your envelope, and you now have a tight binary consisting of a black hole and just a stellar core, say a naked helium star. And now it's not a problem at all to have this binary be only a few solar radii in separation, meaning you can eventually have a merger through gravitational-wave emission. And if you thought that was magic, the second option is a bit more magical. The second option says it involves a magic wand. Abracadabra, stars, thou shalt not expand. Stars listen. The way that you prevent stars from expanding, right? Remember, the problem with this whole story, right? Is stars expand to be several astronomical units in size, and you want to end up with two compact objects that are only a few solar radii, a few tens of solar radii apart, right? So how do you prevent stars from expanding? I say stars, thou shalt not expand. The reason you're not going to expand is the following. Normally you expand, if you're a massive star, at the end or after the end of the main sequence, because the stellar core contracts after you run out of hydrogen. And by the mirror principle, the envelope expands in response. And the way to ostensibly prevent that is to say, well, there won't be a core in the envelope. We're going to somehow magically mix the star in such a way that we're bringing in constantly hydrogen from the envelope into the core and fusing it and bringing helium back out into the envelope. So the star does not build up a chemical gradient. In the end, we just convert the entire mass of the star from hydrogen to helium. So at the end of the main sequence, instead of expanding into a supergiant, we just end up with a Wolf-Rayet star, helium star with a very small radius, problem solved, eventually collapses to a black hole, makes a black hole in situ. So we start with a tight binary, we end up with a tight binary black hole. Great. Why would the star be so efficiently mixed? Well, one possibility for this chemically homogeneous evolution is that maybe it's in the fact itself that the binary was closed to begin with in this story that actually enables you to have chemically homogeneous evolution, because the stars, when they're in a closed binary, are tightly locked, they're forced to rapidly rotate. We're talking about orbital periods of order 1 or 2 days. So that means you have also spin periods of 1 or 2 days. The rotation is rapid enough that you end up with a very different temperature at the equator and at the poles. So you create circulatory motions, energy-sweet circulation, for example, and this is allowing you to mix material between the outer and inner layers of the star. So Pablo Marchand, Philip, and collaborators have proposed this in particular for binary black holes in early 2016, and Selma Domink and I had a independent proposal in roughly the same time scale for these systems. Whether or not it's really all that efficient or whether it even really happens is, I think, still an open question, but at least that's a possibility. The third possibility, by the way, is dynamic information. You can think of that as a kind of black hole matchmaking club, Tinder for black holes. So the idea is something like the following. You put the black holes you don't put them necessarily initially binaries with each other. You put them in some dense stellar environment, like a globular cluster, where there are plenty of opportunities for interaction. Maybe the black hole is initially actually with a different companion, a low mass companion, but another black hole comes along. You have a 2+1 scattering interaction. In those interactions, typically the lowest mass objects get ejected, the highest mass objects stay together. So you end up with and the binary gets hardened over time through multiple interactions until gravitational waves can take over. So these are at least some of the possibilities. Now, I have 3 minutes, something like that. Yeah, okay. So I will skip the story of what makes high mass black hole X-ray binaries observable, except to just say one thing on this. So why do I mentioned earlier that I think we know the answer, thanks to some work by my amazing colleague Rio Hirai, who has really figured out this problem. But the answer to why in a wind-fed system with a black hole, the companion has to be very close. The answer is actually that if you want this to be an X-ray binary, you have to have an accretion disk. Otherwise, you're not efficient in converting the gravitational energy into luminosity. You want to have an accretion disk, you have to have enough angular momentum to form a disk. And remarkably, it turns out that even a typical wind-fed system with spherical winds coming off of the donor, you don't have enough angular momentum to form a disk. And the only way to actually get enough angular momentum to form a disk is to have a donor which is significantly tidally distorted enough that you have gravity darkening, which is changing how much mass is lost from different parts of the star, but also because these are line-driven winds for O stars, changing how much acceleration there is. And the changing the acceleration means that you have a very different wind velocity profile. And the change in wind velocity profile means that now, if you do the calculation more carefully, you find that in those systems which are almost Roscoe filling, therefore have this changed wind morphology, they're exactly the ones that can actually have enough angular momentum in the winds to create an accretion disk, and therefore to be potentially X-ray bright sources. I will have to skip some of our work on modeling supernova masses and kicks, as well as on common envelope evolution. So my apologies to Mike. This was going to be Mike's movie. Maybe, well, I'll just show Mike's movie. So this is Mike's movie. Mike, prior to joining the group here, was working with Rio, Daniel Price, and myself at Monash, and has been doing some common envelope modeling. And here's an example of a companion spiraling into the envelope of in this case, a red supergiant. And you'll see that at least parts of the envelope will be ejected here, and the companion is, of course, going to sink much closer towards the center. In fact, some of Mike's simulations have also prompted some analytical work by Rio and others, and we think we might have in addition to the various insights gained directly from the hydro modeling, we might have also a more analytical model of what might be the outcomes of common envelope evolution. Won't have time to talk about that, but people who are interested can ask me about it. So we are calling it this two-stage formalism for common envelopes, where it's a mixture of energy conservation and angular momentum conservation essentially applied to different layers of the envelope. So by way of a summary, let me say that I instead of doing a proper summary, I like making scientific bets. For people who have met Kip Thorne, you may be aware that he has a long history of making bets, and so I think out of the many things he tried to teach me, it was the only one that I actually managed to learn. The first scientific bet I made was actually a bet with Kip directly, because back in 2010, we thought we may have had a gravitational wave detection. The bet was whether it was real or not, because it could have been a blind injection set up to test the instruments. I bet that it was Kip. Kip was an optimist and bet it was real. I was a pessimist and bet that it wasn't. With great sadness, I hereby concede Kip Thorne. But on the bright side, it did mean that gravitational waves would just be detected a little bit later, and of course they were. As another example, this time I was the pessimist. I bet against Niels Tanver in 2013 or so that none of the first 10 gravitational wave detections would be accompanied by an electromagnetic counterpart. GW 170817 was one of the first 10. I claim I still made a sensible bet because now we have more than 100 and only one of them has had an electromagnetic counterpart. So I think statistically I was right, but I'm perfectly happy to have lost this bet because of course it was a wonderful event and I'm very happy to have been part of some of the analyses of the data from that event. There's some bets about whether or not the mass gap was filled in and so on. And of course, there are plenty of more bets that are still coming up related to, in particular, gravitational wave observations. So, for example, what is the nature of mass gap objects like GW 190814, which had a mass of about 2.6 solar masses? Will there be eccentric system observed in the LIGO band? There's some tentative evidence that maybe some people have claimed that they've seen evidence of eccentricity. I don't think it's particularly convincing yet, but perhaps in the not too distant future, we'll be able to resolve this bet. And of course, there are a number of others. So this is simply a statement that there are plenty more things to discuss and debate and to look forward to, ultimately to learn from the data. So it's a field that's continuing to be very exciting, and hopefully at least I've shared some of my excitement with you. Thank you.
I just move a bit close to the microphone. Thank you very much, Ilya, for your insights and those rather intuitive explanations for those of us who don't work in the field. I think we all very much appreciate this, and we certainly will have questions following up on a number of those things. There is already one on the from the virtual audience, but first of all, I would give the opportunity to the floor.
You want to say a word about
Yeah.
this slide?
Yes. Well, no, we'll do.
Oh, do it later.
We'll do
Okay,
that
I'm
later.
sorry. I'm sorry. Okay.
That's next week's colloquium, but we'll do that later. So questions for Ilya, please. I don't see anything. Oh, yes, there is. The first is up on the top. Right. We've got the drill.
Hi, Ian. You spent a lot on Monash because of the model by Kai, and it's very beautiful model, but now we know that stable mass transfer can also produce efficient mergers. So can you expand on it? What is your bet about stable mass transfer and common ability? What's going on?
So my current best guess, with some things remaining to be tested, is that for the common envelope channel is still critical for binary neutron star formation, for the formation of closed binary neutron stars that are ultimately merging, but that it's probably not a significant contributor, possibly not a contributor at all for binary black holes. So binary black holes, they may not come from isolated binaries at all, but those that do probably come through arise through the stable mass transfer channel.
Okay. Okay. Question, please. Don't see anybody, anything here, so I'll move directly and read out the question, which is from James Bell. Would you need a larger filling factor for the B-type star companions for the X-ray binaries then due to the weaker winds?
So that's a very interesting question, right? So we don't all of the black hole hemisphere binaries are have with winds have O star companions with line-driven winds. What would happen with B stars? I think is an interesting question. Yes, the winds are weaker, and but I think there's that just in general, weaker winds will overall decrease the total mass accretion rate, and and of course, if the mass accretion rate is too low and is very significantly sub-Eddington, you have another problem, which is that perhaps you are no longer in this in a moderately efficient regime, but instead you may have some advection-dominated accretion flows, for example, which even if you do have enough angular momentum, you might have very low luminosities. So that absolutely is a possibility. I hesitate to say. I mean, Andreas has I think maybe a comment to make on this. So please go ahead.
Okay.
Well, the point with the non-high-mass-6 binary is that I wouldn't a priori agree that the B stars, the one with B star donors, have that weaker winds. So of course, if you compare an O main sequence star to B main sequence of the B star, will have a weaker wind. But usually, what you have in the high-mass-6 binaries are the supergiants. So you have stars that are evolutionary people stars that are overlooked, and that means they have a stronger wind. So actually, we have systems which really quite strong winds. And most of the high-mass binaries are all in this late O, early B type regime. And it's probably a case-by-case situation whether the upstar actually has to start on it. I don't think that this is necessarily a problem for the systems.
Thank you. I have a question actually about the black hole binaries. You mentioned Roche-Rosenberg filling was approaching unity. And you were going to tell us why that is, but you didn't.
Oh, right. Sorry. So that was indeed this plot over here. So the story here was that so you can see over here how much angular momentum there is. Ignore the various curves. Let's say focus on the solid blue line, right? So this is basically saying that the specific angular momentum is in the summit arbitrary units is quite low, 10 to the minus 5, 10 to the minus 4, as you are only 30%, 50%, 60% or so filling, and then you see that there's this very sudden jump right around 80% or so filling, where it goes up to something like 10 to the minus 2 in these units, where 10 to the minus 2 is roughly the threshold for having enough angular momentum to form a disk, meaning the specific angular momentum has to be at least as large as the specific angular momentum at the innermost stable circular orbit, right? And the reason for this is basically that you really need that tidal distortion of the star in order to change the morphology of the wind because of the change in where the mass is being lost and what the acceleration profile of the wind is.
Okay. Sort of get a picture of that, yeah. So you can't get this as you really start this board, and then it's
exactly, and otherwise you just have this, spherical accretion if you don't have enough angular momentum, and so you can imagine, the mental picture I have is of one of these, amazing Olympic divers going from the 10-meter board and hitting the swimming pool, but not making any splash because they're so good at this, right? So of course they have their potential energy, they convert it into kinetic energy, but then it all goes into the pool and never appears above the surface of the water, right? So if you have spherical accretion, there are no shocks, everything, of course, yes, you still have gravitational energy, but it just all advected into the black hole, and sinks inside the horizon, right? It's only if you have something interesting happening outside the black hole, for example, in the accretion disk, right? You've got viscosity, you can generate energy that will actually power some light coming out, right? And so you need to have matter sticking out outside of the event horizon for a while in order to do that, and that means you need to have enough angular momentum.
okay, thank you. At the front here.
Thank you. if there is a precession of the orbital angular momentum of the two black holes, is that indicative of the history of the black holes in the sense if you have little precession, you would expect that the two are produced together, and if there's a lot of precession, they should be produced individually. So first of all, is that true? And can you measure the precession of the angular momentum?
That's a great question. So yes, in general, that's absolutely true. So we would generally expect that if we have, if the binary is evolving as a binary, there are multiple things during the binary, multiple interactions during binary evolution, which ought to preferentially align the two spins. So mass transfer between components will generally align the spins. Tides can, if tides are efficient, can align the spins. So you expect to have preferentially aligned spins. If you have two black holes that, for example, come together through dynamical interactions, then there's no particular reason for the spins to be aligned. In some cases, you actually even have preferred misalignment. For example, if you have a hierarchical Lyapunov triple, then you actually expect the spins to be preferentially misaligned. That means that, yes, in general, this should be the degree of spin orbit misalignment and therefore precession should be a signature of the formation channel. So far, there is only been a claim of one event with a relatively confidently detected precession. And even there is some debate because there's also some noise glitch overlapping this event. So it's a little bit uncertain whether we can separate out the noise glitch well enough to confidently infer the precession. The LIGO-Virgo collaboration has claimed that even though very few individual events have strong evidence of precession, the population of events, there are enough events with mild evidence of precession that together there's evidence that precession is not uncommon, but that's a possibly debatable statement. Let's say I'm not personally convinced by that particular statement. So I think there's still some room for debate as to whether or not we have sufficient evidence that there's a precessing subpopulation. But if there is a subpopulation with strongly misaligned spins and orbital angular momenta, that I think would be a strong argument for dynamical formation playing a role.
Thanks.
Okay, well, with that, I think that we're approaching time to wrap up. And before so again, Ilya, thank you very much for